Well, if there's no more questions, I think we can go ahead and move on. Next speaker is Dr. Craig Gartrell, who was with Contra Costa Water District, but is not.
Yeah, no, nice and retired, so I have time to think about things. I'd like to start off by saying that I hope, if I do this right and am as clear as I intend to be, I will help resolve some of the issues that arose yesterday. There was some confusion of what is important. Is it exports? Is it OMR flows? And get into the relationship between those two. There are a lot of other things that came up yesterday and today that will be explained by some of the things I'm going to discuss. For example, why there is a zone of influence, what that means. I'm going to get into some concepts that haven't been tossed out at you, but it gets into what Bruce did mention them, a riverine kind of system or regime as opposed to tidal, and there's another one in there you'll see is transitional. I'm going to touch upon the importance of velocity. I was pleased to hear that put out a couple of times as it's velocity, not flow. The first time is actually extraordinary. The first time I mentioned this a number of years ago to a person at Fish and Game that had been around for a long time, is that, look, the fish don't respond to flow. They don't know what flow is. They know what velocity is. He looked at me like I was from Mars and speaking a foreign language, and which says how you can get into a mindset or an ideology of what's important because you were able to measure it. But if flow and velocity are certainly related, but they're not the same thing. But I'm going to focus on what the important variables are and why. I'm going to put some focus on dimensional analysis. Throughout this whole 2 days, I've seen very, very little in terms of dimensionless parameters. I did see one this morning on that exponential. If the omega, it didn't say what the units on that were, but if the omega on that exponential or velocity, then that was with that 1 over lambda, that was a dimensionless parameter, and that's important. And I'm going to let's see if I get in. Yes. Get into the first slide on that. Why are dimensionless numbers important? Well, they aren't if there's no sea level rise. They aren't if we're not going to change channel widths and put in setback levees. They're not if we're not going to change habitat and put that in. They are if you are. And all those things are planned. If the delta is going to stay exactly as it is right now, then you don't need to bother with them. You can just put all your parameters in terms of dimensional parameters. I did like to, Buckingham's theorem is now 100 years old, and nonetheless it's still largely, in this context, and I've seen this before, I raised this a number of years ago with the National Research Council Committee, still don't automatically look at things in terms of dimensionless parameters, even though it's the correct way to do that. Physics just doesn't depend on whether we use cubic meters per second or cubic furlongs per fortnight. But it does allow, in this context, you'll see a characterization of the flow regimes, which is I'll show is important in understanding this. So first thing you got to take a look at, of course, is order of magnitude. Yes.
Isn't EI ratio a dimensionless parameter? EI ratio?
Yes, yeah, there's one.
Okay.
There's one. And I will even violate my own reasoning here in law later on, as you'll see. But what I'm trying to do there is compare two ways of doing it, and I'm comparing to the way that's been done in the past. Not saying that's the way to do it. Okay, well, the important things, obviously the tides are important. In the channels I'm looking at, I'm focusing on Old and Middle Rivers and actually Indian Slough and San Joaquin, close to the export pumps, and looking at salvage tidal regimes and the important parameters. You're plus and minus 400 cubic meters per second, or plus or minus 15,000 cubic feet per second in any one channel. That gives you kind of a range on that. Export pumping can be on that same order of magnitude for any one channel. at its highest. San Joaquin River flow, that varies all over the place, but for most of the time, it's in the lower regime. It's only when it's flood conditions. You saw that in some of the graphs yesterday, that we've plugged that whole system up with dams so effectively that most of the time it's very low flow conditions, but it is significant compared to the others. Then there's agricultural diversions in the South Delta. They can be fairly significant in the summertime. In the data that I'm showing and focusing on here, which is in winter and early spring, they're generally not. They could actually be negative in that point. They're pumping more water off the islands than they're taking on. And then there's some minor diversions. One from the agency I used to work for, and they're very much smaller. In fact, CCWDs is screened, so they have a different effect. They take water but not fish. So in terms of dimensionless parameters, what I'm going to choose here is a parameter that is based on the, just to start off, to look at the tidal regimes, a parameter based on the amplitude of the tides. And I'm using combined amplitude Old and Middle River because that's convenient to compare with a lot of the data. Again, but for a fixed system, whether you look at flow or velocity doesn't matter. It comes out the same because of the cross-sectional areas. It comes in there, and that just cancels out. But what I want to look at is the tidal amplitude. And so I'm going to kind of, before I do that, though, I'm going to, in terms of what parameter, what this flow index is, or the velocity index. That can be an average, it can be OMR, it can be some other things. But I'm going to take a little simple look here in a second, using a continuity argument that kind of sets that stage. So where I will be looking at, we have meters here and here that I'll be focusing on. There are actually some others down here and here. That can also be used. If you think in terms of fish salvage, yes, some normalized salvage, based on, for example, the fall midwater trawl population estimate or something like that. And the flow out on a continuity basis has got to be the flow in coming in from the north. That's not just Old and Middle River flows. It's also this channel 2 Indian Slough, which we'll get into what its relationship is just on a continuity basis. And then flow coming in from the east, I'm calling it north and east in this case, flow from the north, flow from the east. And then there's going to be a certain density of fish coming in from that direction, a certain density coming in from the north. Well, you can see immediately the two continuity coefficients, one's just on water, one's on fish population, or related to the fish coming in there. And it doesn't, in about 2 minutes, you can write down this equation. Which is dimensionally correct. And you can see right away why there is it's exports, no, it's Old and Middle River flow. And you'll see this in a subsequent slide, but if you take the density of fish to be 0 coming in from the east, for example, Sacramento River salmon or Delta smelt, which largely aren't on that side, then the term in the brackets is related to Old and Middle River and Indian Slough flow. But you have that Q export out in the front. I'll get into that a little bit in a minute. And you have this factor A, that's the fraction of flow coming over from the San Joaquin River. It can be either just the measured flow that comes through the head of Old River, or it can be reduced by the agricultural use in that area, however you want to run that. But you can quite quickly take some limiting cases on that. First of all, you notice that a trick you can do to reduce daily salvage is to reduce your exports. So if you have a certain number of fish density in the area and you're running up against your limit for the month, you can turn your exports down for a couple of days, and you can actually see that on the data. And this occurred I'll describe it a little later, in one of the years that Pete Smith discussed yesterday. So right away you see there's a strong relationship with the exports. In terms of order of magnitude, the minor flows are on the order of 1 or 2%. Those are much less than 1, so you can safely ignore that to begin with. But we'll come back later on and compare when you put that back, all that stuff back in, what that does to your data analysis. The San Joaquin River times is factor A. A is on the order of a half. And the San Joaquin River over the exports, that's the combined value of that 0.5, and that typically is going to be on the order of 0.1, so that's relatively small. Can be big, and it can go the other way. A lot of flow coming over there overwhelm the exports. When for San Joaquin salmon and steelhead, this gets into something that Brad Cavallo was discussing yesterday. Well, it's just exports. It's not Old and Middle River flow. Well, that's actually, you see that if for San Joaquin steelhead, where the density of fish coming from the east and the north might be on the same order of magnitude. In that case, it really is just the exports. It doesn't matter whether they're coming in from the north or the east. It's the total exports that counts. And you should be able to see that in the data. I don't know if anyone's done that, but I'm going to show some graphs that don't do that later. But my suggestion is that, like his, it's something that needs to be looked at. For Delta smelt and Sacramento McKelney salmon, then you have it's not coming in from the east, it's just coming in from the north. We haven't said anything about what this row is yet. Let me discuss that. But that relationship down at the bottom is more related towards an Old and Middle River flow. It also includes Indian Slough, but we'll get into that in a minute. So what about this row N? Well, that is the density of fish coming from the north. How do they get there? It's a local value when they're actually salvaged, but it depends on what's been going on in their whole travel. In fact, it depends on, if you like to think in terms of electromagnetic fields, a retarded time or antecedent conditions. Something happened earlier someplace else, and they work their way down, and they get there. It has survival and turbidity or other factors that may be in there, but in some sense, they took a trip down those rivers, and you really should be integrating over those rivers, and that immediately suggests a Lagrangian framework rather than an Eulerian framework to understand this, and I'll get into that in a minute. So what parameter to use for this flow index? I want to just focus on the important parts first, and then we'll get back in and look how the other parts that we're leaving out affect things. So we start with a normalized version of that, dividing by the flow amplitude, and you can rearrange that. The term in the middle there, the Q exports minus the A times the Q San Joaquin River, that with the A out there, a factor there, is very much related to Old and Middle River flow. It's pretty much the whole thing. When you do a regression to relate that flow index, which is just the exports in the San Joaquin River, to Old and Middle River flows, you get a factor of 0.87 and about 0.48 for the case with no berries. You get some different relationships, but you get that 0.87. So what does that mean, that 0.87? Well, if you take the case where the San Joaquin River is small compared to the exports, nearly all the flow is coming from the north. That means that Old and Middle Rivers are giving you 87% of the export flow, and the other 13% has to come from Indian Slough. So automatically you have, just from that simple analysis and a simple regression, an estimate of how much is coming from Indian Slough, and that's one of the things you're leaving out. Does it matter? We don't know. We don't measure it. But that's why the focus is on those two rivers. If you had a measurement value over there, it would probably be the Old, Middle, and Indian Slough bill. OMI are. So let's take a look. Now we're going to shift into what I mean by a flow regime. I just took March 2014 to take a look at this. This is at the location where the Old and Middle River flows are calculated and measured. I just want to, let me go back. I want to point out, unfortunately there's a dropout here, but during this period here, between 10 and 15 days, you still had a substantial ebb tide at that location, but slightly downstream at near the Old River Highway Bridge. This is a couple of miles downstream. During that period, you actually went into a period where, and this is when there is a little bit higher pumping, there was no ebb tide or very, very short ebb tide. So that immediately, when you look in this, you don't really see that it all looks tidal. There's a big tidal component. When you get to a Lagrangian version, which is basically taking records like this in velocity and integrating them, you get information like this. Now, in this case, that QI over QA, the flow index that depends just on exports in the San Joaquin River flow, as exports is reduced by the San Joaquin River flow, basically the flow coming from the north, compared to the tidal amplitude is minus 0.4. That's for the whole Old and Middle River system. And I'm retaining this 0.87 through this, so it's easy to compare with Old and Middle River flows when we do comparison later. In this particular channel in Old River, where these data come from, it was also minus 0.4. And what you see is if you're following a fluid particle, it's quite riverine. In fact, as you get closer to the location down Highway 4, you've lost totally that ebb. So you're taking a one-way trip here. By the way, the distance here is the approximate distance between Frank's Tract in the north, the beginning of where Old River, if it were in the olden days, the downstream end. And the length I've normalized to is the distance between there and the export pumps, and I stopped the integration at -1 for obvious reasons. It's time to get off the bus and get on the truck to go back to Antioch. On the other hand, if that value of the QIA is minus 0.1 and in the river is minus 0.08, and you'll see in a moment why I'm telling you what's in the river, going on in the river as well as what's going on in this system, it's very much different. It's very much tidal. It took a lot of tidal cycles. These are in time in tidal days, actually, to get down there. You still get there. There's still enough drift. So this is the particle tracking. But it is very much tidal, and there's a lot of integration going on over those many tidal cycles. So what is a transition? This is where it is somewhat surprising, and it explains something that Matt Nabriga mentioned yesterday. This is kind of in between minus 0.3 in Old River. It still looks kind of tidal here. There's a kind of strong drift, but in this channel, this is less. This is getting down to more tidal. But if you look over in Middle River, at the same time that this is going on, same period, it's quite riverine-like. It doesn't take you very many days to get down there. And this doesn't all. And then when you look at what's going on that channel, it's minus 0.35. It's more riverine-like in its own system. So what is going on here? Let's just stop and think about this. Are the export pumps sucking the fish down there? Well, they can, but not directly. They're interacting with the tides, and this gets into the discussion yesterday. Well, is it the tides? Is it tidal? Yes, it depends on where you are. If they are pumping so hard, which they can pump as hard as the tidal amplitude in any one of those channels, then they have turned that into a largely riverine system, and yes, you got a one-way trip, and you don't do very much going back and forth. And if you are a fish that is depending on moving somewhere else by following the tides, you've got a one-way tide, and you end up down there. Once you move down in the export pumping range, you get back in that tidal system, and a whole lot of other things can go on in terms of how the fish react and how they move around. Can you see this in data, for example? And the answer is, yeah, I think so. This is, again, a particle. We'll start with particle tracking data from two locations, one right above Frank's Tract, and another one to the east, where another parameter, Q West, has often been attempted to be used to describe the system. Initially, it was attempted to use that to describe salinity intrusion. It's the net flow in that channel. With the problem with it, and it never worked for salinity intrusion. And the problem is that you're largely down in a regime where QIOQA locally is very small. It's tidal. And if you ignore the tidal dynamics, you're not going to get it right. And sure enough, even when pumping is very, very high, you're still very, very tidal. Any particles down there do have a direct route into Old and Middle River, Steve knows about this, they go through False River, it shoots them right in there. A third of the flood flow on the San Joaquin River at that location goes through False River. So you got a good chance of getting in there, but it doesn't necessarily mean that you do or you get down there if you're just a neutrally buoyant particle. You get down over into a section where there's more influence, the tidal amplitude is smaller locally, more directly influenced by the pumps, and when you get into the minus 0.4, lots of particles get down there. When you stay in the tidal regime, a lot less. Do you see this in the fish salvage data? Yes, you do as well. When you're down in this region, which is very riverine-like, you get lots of salvage. I'll explain these data in a minute. When you get out into the more tidal regime, even when the net flows the wrong way, you still get salvage waves because it's another dynamic is going on with the tides. So you can use this parameter to kind of see where you are. Probably a good thing is to avoid this area, especially when there's high turbidity. Back on this, what was going on here? This is one of those time periods where it was the 2002-2003 time frame that Pete discussed yesterday. They got to the end of the month, they were getting up against their limit, and they turned the exports down. So when you plot this, what I'm going to argue against later, on a daily basis, this is the daily salvage versus the daily flow index. On that day, yes, the numbers came down, but that's really not the way to look at this because the fish are coming in on an integrated basis. They're following a path that integrates over time. We'll get into that a little bit more in a minute. So we've seen what we can do with just those two variables, which are very much the largest. They're also dependent implicitly on a third factor, which is barriers. But there are those three things: the San Joaquin River flow, the exports, and the barriers are things that the projects can control. The other stuff is stuff they can't control: the minor flows, tidal effects. But let's take a look at in terms of salvage, what the stuff we left out, if that has a trend in salvage. You would expect that when Old and Middle River flows, the measured numbers are very much more negative than the index, which will happen on certain parts of the spring tidals. You get a lot less salvage, and when it's the other way around, it goes the other way. So you get more when it's more negative, less when it's less negative, and you don't see that. When you look at that, and this is non-dimensionalized, I'll show you the dimensionalized, or dimensional, I'll show you because I was looking at every which way to see if you could see any trend. I'll show you the dimensionless version of this in a second. No, it's the red line is bin stuff, so just in case your eye's being fooled by the scatter of data, it's quite flat. It doesn't matter. All the other stuff that you're getting out of the daily measurements of Old and Middle River flows is giving you basically noise. There may be a signal in there, but the noise is overwhelming it. If you normalize this, use a normalized delta smelt, it piles up in the middle. Well, you'd expect that because all your big salvage is when you have the riverine conditions, when the exports are very high. You divide by the flow index, which is very much related to the exports. It's going to push all those data in there. But what I was looking for here is, well, is it important? Maybe it's not important, these flow fluctuations or other things going on when they're pumping hard. Maybe it's just important when you're not pumping hard and Old and Middle River flows are small and the flow index is small and the fluctuations are big by comparison, you still don't see that. So let's think about this. So what's going on? When the flow index, when exports are really big, they're taking a fast trip down there. And when you have this flow fluctuation on there, they take a little bit faster or a little bit shorter trip. Does it matter whether they get there at 3 p.m. or 8 p.m. on daily data? No, they still got there. So when in the really big export periods, no, it doesn't matter. Well, what about the other periods when they're pumping less? Why don't the fluctuations matter then? That's when you're integrating over many tidal periods. And the flow fluctuations sometimes are high, sometimes are low, but on that whole trip, they average out. So you don't see it there as well. So that's my argument for why you see that scatter. You're not seeing, you can be chasing your tail there, trying to chase the daily fluctuations. It's going to, you can probably see that I'm going to get into, maybe we should start averaging this, and you'll see that in a few minutes. So what would you expect when you compare these same data I showed earlier with old and middle river flow? Well, you see more scatter. You see it's quite tight because you're only focused on one parameter when you have the flow index, and more scatter when you don't. But you're not necessarily getting more information. They're both still telling you, stay out of this high turbidity regime with riverine-like conditions, get over into more tidal conditions, and you're going to reduce your salvage. Same thing is true with the particle tracking. They look very, very similar. Same data, just plotted two different ways, one on what the OMR was at the time in the model, the other one on the flow index. But these are integrated over a longer period of time, so you don't, you're not going to expect to see much. You should see them very, very close anyway. And you see the same thing in field data with delta smelt salvage. When you integrate that over a long time period, December through March, that's the total salvage over those time periods, versus the average of the OMR or the average of the flow index over those periods. Yeah, all that stuff, what it's saying is it's small, it doesn't matter. You can come to the same conclusions on either case. You saw this yesterday. This one was the one that Matt showed. And again, you see the data become much tighter when you're using the flow index. Again, these are on daily data that haven't been averaged over any kind of a time period. Well, you can see what the issue might be when you start averaging over these time periods, what period to use. It's really a function of what's going on in the channel during the time. You basically have to take the velocity, integrate it back into when you get the right distance, that's the time frame, and then average the velocity over that time. That tells you both the tidal regime you're in, but it also tells you what the influence on the particles. This is the one I was mentioning before. This is with steelhead salvage. This is the one I think that it probably is better to plot this against just the exports rather than OMR. But you can see, again, the important thing is you have, when you get over in the range when it's largely riverine, you can get lots of salvage. You don't have to get lots of salvage. If there are not very many fish around, the row's small, you get very short. But you don't get lots of salvage when you get over in the tidal regime. So let's take a look at filtering for a minute in time averages. This is from last fall, and I picked it because it had a varying export during this period. But what this shows is the combined old and middle river flows, along with the Godin filtered the Godin filter average along here. And what I want to show is what different. One of the problems with the Godin filter is that it's centered. So when you're plotting these data, you immediately have a problem when you're plotting these data on a daily basis because it knows what was going to happen, and it's saying the fish, which were only affected by things that did happen, are going to be affected by things that haven't happened yet. You can get rid of that by doing a backward filtering or just running average. What I did here is took the black line is the Godin filtered tidal data, and then I used this blue one that's still going up. You see, it's about a day lag or half a day lag. It tracks it. That's a 1 day running average of it. The red is about a 3 day running average. That's about the least amount of averaging because it's going to take anybody coming in from the north at least 3 days to get down there, 3 tidal days. And then the brown one is a 7 day. And with the 7 day, you've already eliminated a lot of the tidal fluctuations that you have already seen, or just adding noise when you're looking at these data. So how does that compare with the flow index? And this is also quite interesting. Again, this is the Godin filtered tidal data the black line. And the red line is the daily numbers, that flow index on a daily basis. Some of this is they really changed, they turned the pump on and off. Some is, well, the head was, it's over a 24-hour, the head was a little bit different. They had the pumps on the same, but they got less flow. But you do see that the fluctuations, the old and middle river flow are picking up those fluctuations. But if you do a 7-day average on, a 7-day running average on both, they can turn out quite similar. So you might expect that when you start looking at, I picked 7 days not just out of a hat, it's when you get into that regime where it's kind of at the low end of the transitional, in the regime where the projects are now directed by their biological opinions, it's a 7-day or longer averaging that's required to examine the data. Well, then you look at the data with OMR or the index, and they're over that 7-day averaging is quite similar. Again, you see those data are hanging out in the breeze over here. Now that you're doing this averaging, because those were very short periods that they turned the exports down and they turned them back up, the flow regime really didn't react that much, and the fish in the system didn't react. And in fact, they don't operate this way anymore for obvious reasons. They're more down in this range now, but that you can see that it comes out quite similar once you start doing that. So let's go back to that other plot I had. Do we get more information now that we do a 7-day average? And the answer is really not too much. It's still, this kind of surprised me. I thought you'd see something in this. This is normalized, and you see less scatter. If anything, you see some odd points hanging out in the breeze here that the index is saying is much more negative than OMR. I'm not sure why that is, but they kind of go away when you normalize. So, but you don't see, you're still not getting a lot of information from OMR compared to even the flow index. You're not getting additional information. You're getting a lot of noise. So you have to be very, very careful in using the field data on there. You may fool yourself. You may feel good. We're gonna follow what the flow meter says, but the data don't support that you're actually doing something one way or another when you're doing that. So in conclusion, I say normalize the velocities for flow regimes so you can have an idea what you're going to do in future changes. Why is that important? A flow of 10,000 cubic feet per second might sound big or small depending on where you are. But if you change you put in habitat restorations that squashes the tides, you can turn, which you see in some of the modeling for South Delta habitat restoration, you can change yourself from what was tidal into riverine real quickly by using the same numerical value for flow and not looking at it in a normalized way. Clearly from this, the important parameters, the tidal amplitude, export, San Joaquin flows, and whether or not you have barriers in there. It's clear you want to avoid the riverine type conditions to avoid large salvage. For San Joaquin salmon and steelhead, it needs to be looked at, but the exports themselves are probably more important than old and middle river flows. The Lagrangian time frame suggests that the averaging time that you want to look at in terms of analyzing data, you don't want to use daily. You're just adding noise to it. Comparison of the measured OMR and QI indicates two things. You're leaving out, of course, Indian slough. You're not getting all of what the export effect is in there by leaving that out. But it doesn't, in terms of the fish salvage, it's not adding a whole lot of information. It can be adding noise, and you have to be cautious of that. The other thing in terms of regulatory, the index with the San Joaquin River flow, the exports, and the barriers in there puts the emphasis on the factors that are actually changing the flow regime. None of the other factors can change it. You can turn on all the South Delta ag, which is the next biggest thing. You're still not going to change the flow regime. It's the one that's directly related to salvage. If you use that as on a day-to-day basis, then you're putting the focus on what's causing the issue. Doesn't mean you don't look at OMR. You can learn a lot from that while you're doing that at the same time. I think it's kind of stupid to have a meter out there and then deliberately not look at it. That completes my discussion. I hope that helped resolve some of the why is it exports, why is it Old Middle River flow, and what the important parameters are, and helps pull that into focus.
Once I did the algebra myself.
I did it while I was sitting in the symphony and board with Nielsen.
So we are just about at lunchtime. I know you guys all got every word of that, and but if you do have one quick question, we can probably do it. And you're going to be around for the rest of the day too. So,
I guess one question I would have, Greg, when you're sort of showing this tidal variability in the channels, which is an interesting one, does it suggest somehow that the flow standards should be tied to the spring neap cycle?
No, it's
because it averages it out?
Yeah, it's not like, John's earlier discussion where he had that enormous variation. If you go put in tidal habitat and you have that kind of situation, this answer changes completely. But for this system, the way it's set up right now, I think the data kind of answer that question. That when you're not pumping very hard, you're averaging over lots of tides. When you're pumping really hard, it doesn't matter anyway. You got a one-way trip. And the way they're operating now, during these periods when the fish are around, you're avoiding the riverine conditions. You're even avoiding a lot of the transition. That transition, that interesting thing about Old and Middle River, it does explain something that Matt said yesterday. Well, in the particle tracking, you throw particles in on the McKelvey River in the north, and a whole pile of them end up. Well, that's kind of why they come down the McKelvey River on the flood tide. When they come back on the ebb tide, when they come back on the flood, a big fraction will go into Middle River, and then they're gone. In many cases, because it stays more riverine-like longer as you crank down. But I think the regime they're kind of working in terms of it's always in minus 5,000 or minus 2,500. So it obeys Greg's law, which is things that are evenly divisible by 5 and 10 probably aren't based on science. It has to do with decimal system and how many fingers we have. But they're doing in those increments, and at the 5,000 you're in the Q, 5,000 over 25,000 you're in the 0.2. You're down in the tidal. You're in the upper end or the lower end of the transitional or upper end of the tidal and the lower. So you're staying out of that regime anyway. They backed into it, didn't know why it works. This kind of says why.
okay, ready for lunch? So we're going to take a lunch break now, and we'll come back about 1:25.